Well, my name is Eric Solo. I'm from Alpha Power Solutions, and today I'd like to show you how power factor correction works through this little demo unit that we constructed. So we have here a motor that will simulate the inductive load that would be present in a factory or commercial building. We have a power factor correction panel here, and this is just a little control box to manage this whole thing. So basically what you have here, so this is the actual brain. This device is fed with a current feedback and a voltage feedback, and allows it to calculate what the power factor of the load is. Right now, the value displayed here, 0.96, 0.95, it fluctuates a little bit. That is the power factor of the load being drawn from the grid. It is not the power factor of this actual load, it is measuring the power factor of the incoming power. These are just a representation of the 3 steps, and as you can see, it's highlighted. It means that these 3 steps are engaged. This little sign here says that it is in automatic mode, and here the values displayed here is all relevant factors that an electrician would want to see in case of troubleshooting. So you got the temperature inside the panel, the total harmonic distortion voltage, the total harmonic distortion current. The next one is the target power factor, which is 1. That's the shortfall of kilovars in order to achieve a power factor of 1. That's the voltage. That's the amperage. That's the working power factor. And that's it. So these are the values that keep on cycling. This device I've only added so that you can see the current dropping on all 3 phases. So it's a 3-phase system, and because you can't see that information in this little device, I've added a separate meter just to show that the current drops dramatically when you put the power factor correction system on. These are just selector switches that can either bring in the steps or energize the contactors inside the power factor correction panel, and so you can put them in manual or in auto or off. This little meter I've introduced so you can see that if the power factor correction is off, the cost to run the motor is pretty high. But as you reduce the reactive load being drawn from the grid, obviously you pay much less. So it's a representation of the cost reduction that you get when you put power factor correction in. So what I want to do first is start the motor and get things going. So what we have, basically the motor is now spinning, as you can see. There's some current being drawn, and the power factor is extremely poor because right now there's no connected load to the motor. So the vast majority of the power being consumed by the motor is for the magnetic field that the motor needs in order to spin. So inside here we have a bunch of capacitors, and we will bring them the steps in. There's 3 steps in this little demo unit, and I would like you to watch what happens to the power factor and the current. So I'll start with the first 2 steps, and you see by putting 2 of the steps in, the power factor has improved and the current has dropped quite dramatically. And if I increase and I bring in the 3rd step, the power factor improves to almost perfect at 0.96, and there's hardly any current left. So what is happening is that the motor is still consuming the same amount of power, but the reactive power that it's consuming is now coming from the capacitors that are situated inside this box. So the current that's still being drawn from the grid now would be for all the losses, the heat losses, the bearing losses, the fan losses. So it's quite small because there is no load connected to power factor to the motor itself. I also want to show you what happens. This was now done in manual mode, and the controller here had no control over what was happening. So the power factor is still very poor. There's no banks in. The current is pretty high. And the costs for running the motor are pretty high. So the controller is now knows that it needs to do something, and it's waiting for the capacitors to discharge before bringing the steps in automatically. So there's this first step coming in, the second and the third. So now this device had control of the power factor correction. The end result is exactly the same. And as you can see, you know, as far as energy consumption or energy charges from Eskom, this is really dropped down because the reactive power is now supplied by the box and not Eskom. So in a nutshell, that is how it works in a factory as well. Obviously, you would have many motors, the load would be very big, and so this would be a much, much bigger panel, but that is the principle about it. So also this device here, there's lots of, it's actually quite a clever device. You can program many things. You can prevent this unit to operate when the voltage exceeds a value that you have set. The purpose of that is that you don't blow up the capacitors inside. Similarly, you can also set the minimum voltage so that if the voltage drops for whatever reason, there is a risk that the capacitors will start rattling. And with capacitors, it's extremely destructive. Switching capacitors is extremely aggressive. It's one of the most aggressive things you can switch on or off. The capacitors will fight any change. And so if a contactor starts rattling, it actually destroys them extremely fast. So we set the minimum voltage. There's many other parameters that you can set just to make sure that the device operates properly. You can stop it from operating when the temperature is too high. You can stop it from working when the harmonic levels are too high. So there's many, it's a very clever device that prevents damage. So this unit looks after itself if you set the parameters correctly. What we've also started to do is that we now enable our customers to monitor their equipment remotely. What happens typically when you install this panel in the field is that people will show some attention to it initially, and after a while everyone forgets about it. And it might stop working for whatever reason. So we have a device that you connect onto this that downloads the load profile, but also any alarm. So you're able to see the load profile online, but you can also see all active alarms, all the alarm histories, and when a new alarm occurs, people that have been assigned to be notified will get an SMS and an email to say that this particular problem exists. That allows us to send a technician out at very short notice with the right spares, because the alarm will give us an indication as to what the problem is inside the panel. So it's a very useful device that all the big users really want, because they know that you stand to lose a lot of money if this thing isn't operating. So that's an add-on that we've put on. The other thing, and I'll mention it in the presentation as well, is that capacitors represent a low impedance path for voltage surges. So what happens is almost like a vacuum cleaner. It attracts the voltage surge away from the rest of the equipment, but that means that the panel takes most of the knock. And as a result, you save the plant a bit, but you blow up your capacitors. So we always recommend our customers to put class 1, class 2 surge protection to make sure that if voltage surges come true, and it's going to happen more and more as the infrastructure deteriorates, where surge protection on the overhead lines and all that stuff is no longer working, it's very important that you protect the equipment.
I think it's also important to note that this, of course, is a very small unit, and it's just a demo unit.
It's a little demo unit.
Take a look, if we are done with this video, we'll take a quick look at what bigger units look like, just to give viewers an idea or a feel of how big these units are.
Yeah. Well, you will see in the video is that they're quite modular in design. So you can keep on adding racks as long as there's space inside the panel. You can keep adding racks. So yeah.
Okay. Do you want to show us what it looks
Yeah.
like inside?
So let me just switch this all off. So what you have here is basically an isolator to isolate the incoming power. Remember, one thing is that when you install a power factor correction system, you cannot connect this directly onto the main bus bars. This must always be protected by a circuit breaker. We see many installations where this stuff is installed and directly on the bus bar. So you rely on the main breaker to trip in case of an event here. And the danger is, you see, this system is protected by fuses. But if there is a cable fault between here and the main bus bars, somebody drops something on a cable or whatever, you then now rely on the main breaker. So your fault level will be much higher, everything will be much higher, and it is illegal. So you cannot do that. That's the first point that I want to point out. These are the contactors. So they're obviously way overrated for this application, because this is the size of the capacitors. You know, you only need these capacitors to fully correct. So it's, yeah, but we had to do some sort of simulation. So these are the capacitors, and behind each capacitor you will see there is a discharge resistor. So capacitors need to discharge, otherwise they become extremely unsafe, and on big capacitors they store enough energy to kill you if you dare to touch them, if they're not fully discharged. So by law you always have to put capacitors as close as possible to the electrical connection. So they're sitting right behind here. Then I mentioned the fuses, that's to protect the panel. These are the contactors. This is just some resistors to make the system work properly, but so that's not really relevant. What else is there? There's some control fuses here. This is the back of the brain. This is the little meter that showed the cost reduction. This is the back of the selector switches, and that's the back of the little power meter that we have in here. So basically, the key components are, you've got an isolator, you have to have an isolator. You have fuses to protect the system. You have contactors to energize the capacitors. So the total reactive compensation is broken up in blocks, so that you can, the system can bring in capacitors as required. So in other words, as the load changes, it was now a factory rather than just a motor. You'll have motor starting and stopping, so the reactive power usage of a plant is never stable. So you break the total amount of kilovolts needed by the plant, you break it up in blocks, and you tell the brain what the size of these blocks are. So when it knows it needs to increase the amount of reactive power it produces, it will select which of these, in this case 3 steps, which ones to bring in. Similarly, if the load drops and less kilovolts are required, the brain will then decide which of these 3 it will kick out. So it's a completely automatic system. So basically, if the power comes up, this controller boots itself up, and after the program discharge time of the capacitors, again in the controller, it's a parameter that you set, it will then start deciding whether it needs to do something or not. So for example, if there was load shedding and the power is restored, but none of the motors are running in the factory, it will do nothing. And then as the load picks up, it will add. And yeah, so there is nothing that once it's installed, it is completely automatic. There's never a need to change any of the parameters in the controller. They stay there, they were programmed correctly, well, assuming they were programmed correctly, and they will stay there forever. So no one needs to go and do any reprogramming or any of that stuff. So yeah, it's a self-managing device. If the power trips, it will just shut down and sit there and wait. So it's an extremely simple device. You basically have incoming power, some protection, some contactors that are managed by the brain that then energize capacitors. So that's all there is to it.
And that ends up saving a lot of power and
It can.
a lot of a lot of energy.
Yes.
And essentially saving the customer money. And I think in the presentation we'll see we'll get a bit more detail on how it works.
Yep.
That's excellent. Thanks.
And you normally do the programming for the client?
Yeah, we don't. It's kind of it's not overly complicated, but there's literally hundreds of parameters that you can set. Not all of them are relevant, but there's some that are absolutely critical. And when we do an installation, we always make sure that the parameters that are that need to be set, and we know which ones they are. We program them, and once it's there is absolutely no need to change them.